Now I'm going to talk about the welfare measure in inverse demand system. So the first thing I want to talk about is compensating variation. Similar to direct demand system, we will set up like the budget constraints here and see how we can get compensating variations with a change in quantities. So first, this is our original budget constraints. Like the endpoints here are denoted by M is divided up by x1 O, which marks the original level of good 1, and here similarly, this endpoint should be denoted by m over x2 0, which marks the original level of x2, good x2. So now let's suppose that the quantity of good 1 increased to x1 1. So this is an increase. What it would do to our budget constraint is that it would shift it inwards, because now the price should also go down, right? Because it's denoted by this. So it goes down as this increase. So shift inwards to here, and I'll mark this endpoint as m over x1 1. Now let's draw some utility curve. The original utility level supposedly is here, suppose is here, and the original equilibrium point is here, denoted as A. The new utility level goes to here. This is parallel. Sorry, pardon my drawing is not perfect, but you get the idea. This is the new equilibrium level. Notice that intuitively, with a change, like an increase in quantity and a decrease in price, the utility level actually goes up. But it may be a little bit counterintuitive in this graph, but just keep it in mind. It will help you understand. So the compensating variation is to keep the consumer at its original utility level, denoted here as U0, but with the new quantity, right? So we will need to draw a parallel line, a line parallel to this one, but tangent to U0. So like this. Sorry, I will make it up. So suppose it's here. We have our new equilibrium point C, where the utility level remains the same, but the quantity changes. Right? So denoted by Kim, this can be expressed, like CV can be expressed mathematically as, I will explain what this is. So this is the mathematical equation of compensating variation, where this is what Kim's call a distance function. It's actually just a form of utility function, but it uses money matrix to measure it, right? So it's actually, I'm gonna put a money symbol here. So just to remind you, it actually means given the quantity and the utility, how much you need to pay to reach such a quantity and such a utility. Namely, CV is expressed as, now I have the new, so this is the original utility level, the original money that I need to pay. So with the original level of quantity and the original level of utility, that's how much I need to pay. Well, this is that I want to remain as happy as I was, but with the new quantity, and that is how much I need to pay. So this is basically compensating variation. Notice that if this value is smaller than 0, it means that with the change in quality, the quantity, I need to pay less, right? So namely, but with the same level of utility. Namely, I am better off in this change of quantity. Okay, so this is compensating variation. Now I want to put it into a inverse demand curve. I want to show it in another way. Now, I borrowed this entirely from Kim's paper, so I will also use like his graphs and just explain it to you. So he still uses like the coordination of direct demands. It's just like a very slight change, so it should be okay. Now, the original point A marks the original point of original level of quantity. I will put it here. And the original level of price, I will put it here. This marks point A of good 1. After the shifts, let me clarify a little bit more here. So in this graph, graphically, where is CV? It's just basically a shift, this is the original one, from a shift from here to here. So the change here is CV. And put it in here, we'll see a more clear picture of CV. This is, like I said before, the original equilibrium point. And where is C? Well, we don't actually know like the corresponding price level, but what we do know is quantity level, which is the new level of quantity. I will mark it here as this. We don't know about the price, but it's okay. It doesn't really matter. So I'm just gonna put it like here. Okay. Looks good to me. What we do know though is that the price decreased, so it's a downward sloping curve. Mark it here. So this is what Kim's call the compensating. Here is UX. The compensated inverse demand. Why is it compensated? Because along this demand curve, what is unchanged is actually the utility level, but not the budget constraint. So at each level of the quantity, you need to take away the consumer's money or give him money to remain him on the same level of utility. So we call it compensated inverse demand, okay? And what is CV here? It should be actually the area. So notice that now the change occurs with quantity, not price. So the original consumer surplus is basically this part, right? Everything down here. Everything down here. The new level, though, is here. Everything down this line. So here. The difference is what we call compensating variation. This is intuitively understandable because with the increase in quantities and decrease in prices, we are better off, right? So we have more surplus. So it's the area of AC X11, X10. This is compensating variation. Look here, this is like opposite. So don't try to interpret this one and using this one. It would be very confusing. Okay, and okay, that is compensating variation. Let's jump to equivalent variation. Okay, here. Put an EV here. Similar setup here. P1, P2. Original, new curve. This is the original utility, new utility, A, B. Okay, so the definition of equivalence variation is simply that, so what is your willingness to accept or to pay to remain on the new level of utility, but with the old combination of quantity, right? So that said, we need to draw a parallel line, parallel to this one, but go through the new level of utility. So I'm gonna just draw it like this. This, I'm gonna put a D here. This is the new equilibrium point. Go from here to here. This is U0, this is new level of utility. Put it mathematically, is just look like this. Still, we're going to use the distance function. Again, if this value is smaller than 0, it means we're better off. Why? Because we need to pay less. It's the similar idea as compensating variation. We need to pay less to remain on the same level of utility, but with the quantity change, yes. So we are better off. We pay less. So we are better off. That's the idea. Okay. And again, I want to put this one into this graph. Just so that we can have a comparison between CV and EV. Okay, so down here, the EV in this graph can be shown as like the shift from here to here, right? So this part, this shift is EV. It goes through the same utility level, but with difference in price and also quantity, of course. And okay, and so okay, where is it? So like the demand curve of in the situation of equivalence variation should go through point B and point D. Where is point B? Okay, so what we note about point B is this is the new equilibrium point without any compensation after the quantity change. So it has the level of the new level of quantity and the new level of price. Let's denote it as this. This is uncompensated, is what happened in reality, right? So here. And what do we know about D? Well, actually, we don't really know much about it. What we do know is that it is the same level as original quantity, right? It is the parallel shifts of the original budget constraint. So the quantity here, so it should be at the same like vertical line as X10, but it has a slightly higher prices, and which make this line also downward sloping. Looks like this. So this is another compensated inverse demand function with a different level of utility, but it's still compensated. and this will help us to find EV. Similarly, originally, under this compensating inverse demand, originally the consumer surplus is simply this area. But now, with the increase in quantity, it becomes this area. So the difference is equivalence variation, namely dB, the area of dB x11, x10. Okay, right. So this is a graphical presentation of CV and EV. Let's talk about another thing, deadweight loss, or should I put it Marshallian surplus. This is simply a uncompensating situation where there's no compensation happening, meaning the demand curve goes through A and B, right? So the budget constraint held constant while the utility level changes. So just go through like this. This is Marshallian demand, and this is Hicksian demand, as a matter of fact. And so, okay, what is the deadweight loss, or deadweight like a surplus but we will still use deadweight loss, although we are better off in this situation. Is similarly, the idea is similar. So basically, the original surplus is here, new surplus level is here. So the change is Marshallian surplus is basically AB x11 x10, the area of this shape. Okay, so clearly the comparison of these three measures can be made, which is CV smaller than Marshallian surplus, smaller than CV. Okay, so this is like the basic idea of the welfare measures of in Kim's paper presented for inverse demand system. It's quite similar to direct demand system, and from here we will know that if we know the exact form of utility function as well as budget constraint, or maybe I don't know, also like a demand function, like its exact mathematical form, we will simply use like integrals to compute. We can just use integrals to compute like the area, so the actual CV, EV, and MS. So empirically, that's how we are going to do it.